talks this afternoon. The first one is by Sebastiano Carpi, and he's going to talk about conformal nets, VOAs, and the representations.
So, thank you very much. You can hear me with the microphone, is okay? Okay, first of all, I thank the organizer for this beautiful meeting and very nice talks, and for inviting me also to speak here. So, just a few comments on this first page. So, what is the point? So, we had many talks here, and these two words, conformal nets and VOAs, were around, and so the idea is that up to some technical points, they are the same things, but on the other hand, they are the same things because they are two-dimensional chiral conformal field theory from the mathematical point of view, but the mathematics is quite different. So they look quite different, and okay, we would like to understand, to make the more closer than what we see just from some formal aspect of structural similarity, but really look at a more close connection. So what I say here is that this is focused on a joint work with Michi Weiner and Feng Shu. Here, just focus means that it's not only based on this, because in order to explain what we have done and what we would like to do in the future, I have first to recall some recent result I obtained with Yasuka Bagashi, Roberto Longo, and Michi Weiner again. And essentially the idea is this was the vacuum vector, so how to connect the vacuum sector, sorry, the vacuum representation, how to connect the VOA with the conformal net. And the next step is to go to representation theory. But in order to explain representation theory, just not just some definitions, some results, is not complete at all. We have to do what the vacuum is, and maybe I would like to say that when I gave talks on, for example, in Oberwolfach 2 years ago, about this first work with Kawegashi, Longo, and Weiner, I had various people saying to me, and what about representation theory? So it's clear the question, because it's the very important fact. But the point I would like to stress also with this talk, in a certain sense, the vacuum case, so the vacuum correspondence, tell exactly what you should do. Of course, then you have many technical problems to solve. Okay. So there is a preliminary part on, so here just some motivation I essentially give. So we have these two frameworks. An important point is that we are describing only chiral conformal field theories, and chiral means not necessarily holomorphic, so the general structure. And the idea is that to do everything in conformal, two-dimensional conformal field theory, you have to start with these chiral field theories. This is not exhaust at all, but this is essentially the building blocks. These are the building blocks. So the point is the structural similarities are very clear. So you have various proof. Of course, not always we can match them, but for example, we know that we have some rational VOA that gives you a modular tensor category, and we know that in certain cases we have similar conformal net which are rational, and then we have modular tensor category, and we can compare them, and we can, for example, consider subfactors associated with them, and many other things. And the main point is that, in a sense, the approach of VOAs, I would like to say, is mainly, so VOA means vertex operator algebra, and conformal net means something which is done with operator algebras, but the term operator algebra is used in a very different, so not very, but quite different meaning. So conformal nets are done with functional analysis, so the theory of operator algebras in Hilbert space, in the tradition of von Neumann, Gelfand, Naimark, and so on. While vertex operator algebras are quite an algebraic structure. So one work algebraically, and the analysis is not so around. There is some analysis, but it plays a minor role. Okay. Well, so here I recall there is this is a quite long paper where we do the vacuum sector, the vacuum representation, just we compare the two structures, and now we are looking for representation theory. So what I say, I will explain some results I recently obtained. There is a work in preparation with the, also, unfortunately, we have not yet finished. It's part of my fault, but it will be ready, I think, soon now. Just I had some check with Feng. Okay, so I hope you will see soon a preprint on the archive. Well, this essentially, we had various talks with this definition. So yeah, just I would like to point some maybe different name because I need to compare the things. So just to stress the point that the axioms look similar. So I give some names. So we have this conformal net is this family of von Neumann algebra. So we have understood. And I don't go into the details, but say, okay, the essential axioms can be phrased this way. So one is locality, which is a very important one, and also very important for this talk. This means that two algebras associated to this joint interval have to commute. And the other, I don't not give many details, but just want to give names. So one is conformal covariance. The other, I call this energy bounded from below, and the reason why I call this is that in the theory of vertex operator algebra, it's not necessarily positive energy, but it's important that the energy is bounded from below, in a certain sense. And in the unitary case, this is the same. And then conformal symmetry comes from some action of the diffeomorphism group. So actually, the connected component of the identity. Okay. So maybe, since also this we have seen a little bit, I would just make some introductory historical remark, very, very short. I don't know if I'm right. So the main point is that if you look at this definition, it looks quite okay. It's not so familiar, for example, for people who work in quantum field theory and do not know this kind of matters. But actually, if one study a little better things, one realizes that this is essentially an algebraic. This is also written in the first pages of Katz's book. This is an algebraic version of White-Van field theory on the circle. So one should think to these vertex operators as quantum fields, but there is still no analysis there, so one has to put something. So what is the idea? So one have, okay, VOA, first of all, one have many fields. So one have a vector space on which the fields act, but which plays the roles also of an index set. There is this field, state field correspondence. So to each vector, to each state, say there is a field, so an operator. The operator, actually seen in this way, is a formal power series in this parameter Z. And in order to understand the connection with conformal net, we have to think that this Z is actually a complex number of modulus 1. So it lies in the circle. Although it's quite important in the theory of vertex operator algebra that one can move this parameter through the complex plane, here I don't want to see this. So, okay. So we may think this as a Fourier series, not as a Laurent series. Okay, this is the main point. And then there are various axioms that I call exactly in the same way, because in a sense we can make correspondence, and there is a locality and a conformal covariance, and again energy is bounded from below. I don't explain what exactly it means, but essentially there is an energy operator which comes from conformal covariance, and conformal covariance is given not through the diffeomorphism group, but through the central extension of the corresponding Lie algebra, which is the Virasoro algebra. Then there is a special operator which is called L0, which corresponds to rotations on the circle, and this is the energy operator. So energy bounded from below, this means that this operator, which actually is diagonalizable and semi-simple, and the spectrum is just bounded from below. Could be negative, but okay. Maybe the most important thing is the statement of locality, which looks quite strange for people in conformal net, because, and here there is a reason. So what is a quantum field from, in the sense of mathematical physics? So it is an operator value distribution. And here we don't have any topology and any Hilbert space and just a formal power series. And the point is that one may look to this as what is called a formal distribution, for example, in Katz's book. A formal distribution means that, so this formal variable, you can see, integrate against some test functions, and these test functions are actually polynomials in a Laurent sense. So functions on the circle with finite Fourier series. Okay. And when we look only to this function, we don't have functions with compact support. And locality, so in quantum field theory, means essentially that we have a field with smear, with a smooth function. So typically the field at the point is not an operator, it's a distribution. We have to smear with a function, which is in a smooth function, for example, in some test function spaces. And we want to smear with functions which have compact support, so we can localize the field operator in one interval, in another interval, and say that they commute. And this we cannot do with trigonometric polynomials, so we have in a certain sense say that this commutator is, okay, a support when z is equal to w. There's a sort of some delta function, and this is the right way to state this algebraically. Okay, this commutator, I have a problem with the microphone. Okay, I just spent some time here because this is an essential point. And okay, so this is essentially, so when one can do analysis, then this becomes the same as locality in the Whiteman sense and quantum field theory sense. Next step, so maybe, okay, once we understand this, okay, just here, the first comment on this slide, so these fields here are called vertex operators. And the idea is that, okay, another point, when one do quantum field theory, for example, in physics, typically one starts from Lagrangian or something like that. One has a special family of nice fields, which are generators. For example, they correspond to particles and so on. But the point is that when you start with some fields, you can construct many others by doing some canonical constructions and normalization and so on. That is, in vertex operator algebra theory, one used all fields, so all, in a sense, observable fields with certain regularity properties. And this is quite similar to what we do in conformal nets, because we don't use special observables, but the idea is that you use all observables, so all the operators in a certain phenomenon algebra. Even topologically, there we close. Okay. Okay. Yeah, there is a more general notion of vertex algebra, which I will not need in this talk. Okay, now the main point is that, okay, there is something missing in the ordinary axiom of vertex operator algebras, and this we really need, so in order to have contact, so nets of conformal nets is something living on Hilbert space, there is star structure and very important, so unitary structure around, and without this we cannot do nothing direct. We can just look to formal similarity, but if you want really to make contact directly, we need unitarity. So one needs the notion of unitary VOA. This has been done in our paper, but also by Dong and Lin, and okay, there are natural definitions. I would like to say that vertex operator algebra is something, maybe it's not an algebra, so it's not to look as a complicated structure, but it's best to see it as a sort of Lie algebra, maybe, in certain sense, and these unitary vertex operator algebras should correspond to simple complex Lie algebras. This is more or less the situation. So it's a special case, but looks to be very important. Okay. Here's some notation. We have these energy operators. So we have homogeneous fields. Homogeneous fields means that they are eigenvectors for the Hamiltonian, and d is called the dimension or conformal weight of the field. And then, as you before, I wrote this formal power series with the parentheses on the indices, and there is some tradition to homogeneous vector to shift this in order to have an an without parentheses, and here instead of -1 we have -d. This is more close to the physics convention, and it's what we want to use there because it is better for unitarity, so you have nicer formula, more easy. Okay, so from now on V is always a simple VOA and unitary also. Okay. Okay, now we go through analysis. So now we would like to make something. Of course, we have some analysis because we have a scalar product. So for example, we can take completion and a Hilbert space. Okay, but we want something more, which the idea is that it follows from the other things. But we have many other examples where this works, but we have no complete proof. So we assume for the moment, and this is not the most important assumption. So the assumption is that there is a certain estimates, which we call energy bounds, for which the actions of these endomorphisms at this point on this normed space, we have a norm coming from the scalar product. So they are typically, they have to be unbounded operators, but they are not too much unbounded. So in a sense, they are bounded by the Hamiltonian, which is itself unbounded. So okay, and this bounded we require that to be polynomial, but with some power j, which can be arbitrary in principle. So the point is for each vector a, so this constant should depend on a and not on b. So this s, k, and j. Okay, then we take this Hilbert space completion, and now the idea is the following. So we are looking to localized operators, so we want to smear with the function with compact support, and more generally with smooth functions. So thanks to these bounds here, so if you have a smooth function on the circle, so the Fourier coefficients will decrease fast, and take a vector in B and take this infinite series, which now is no more a formal one because will be convergent. So this defines a linear operator on V, and hence on HV with domain V. And then one can show that this is a closable operator in the sense that it has an extension whose graph is a closed subset of the HV, the Cartesian product of HV times itself. So we have a closed operator, and we call this the smear vertex operator. So instead of the variable z, I write here an f, and formally this should be understood in this way. So we integrate the distribution against a test function. Okay, the measure should be chosen in order to have nice formulas, but not so important. Well, now we want to define von Neumann algebra, and the point is that okay, maybe I also spent a few words for people here, which is not comes from functional analysis. So von Neumann algebras are made up with bounded operators. So I can say it's a family of bounded operators, and here we have unbounded operators. Okay, but when the operators are closed, and we have a family of closed operators, but this is very general, one can define what is the von Neumann algebra generated by this family. So there is a notion of the unbounded operator is not an element of the von Neumann algebra, but we say it is affiliated with. It looks like it is. Just to give an example, if we have a self-adjoint operator A, okay, so we know that we can do spectral theorem and, for example, take bounded functions, which typically, for example, the exponential with I, and this will be, okay, a unitary, and this is affiliated with a certain von Neumann algebra M if this operator sits into this, maybe for every real number T. This is a one parameter group. But also for non-self-adjoint we can do this quite in a standard way. Okay, so we have a von Neumann algebra. So it's quite easy, and it's clear that when we increase the interval, so the function with support in this interval is a set an increasing set. Though this here we keep this basic property which is called isotony. So if you increase the interval, we get a larger von Neumann algebra. And if one look at the matter, so everything should come from the other axioms, but locality is a bad point. Locality is a bad point because I've seen that, I've said that, okay, VOA locality is essentially Whiteman locality, so these mirrored fields commute when the function have disjoint support, but from this, one cannot in general prove that the corresponding von Neumann algebra will commute. And this is an historical point in quantum field theory, and so the point was compare Whiteman axioms with some extra assumption with Alcastler axioms, and there is a long history, there are many results there, and say, I think the first paper is by Borchers and Zimmermann, but then there has been important work by Grimm and Jaffe, by Nelson, by Drisler, Fröhlich, and many others, I think. Okay. In general, this is a problem which has no general solution. The very important case, so one can get many examples. And for our point of view, the first thing we do is we give a definition. It should be also said that, okay, so the definition is, okay, V is strongly local if we have no problem with locality. And then we check in examples. Okay, this is not good until we get examples, but the point is that we have a lot of examples. So, and actually we also conjecture that it is always true, but no idea how to prove in general. Well, okay. Then once we assume this locality, then all the other axioms comes from the VOA axiom, so we get a conformal net. For example, this is still a definition, so we are not only assuming unitarity, but it's strong locality property. It's a sort of integrability condition. Well, so the first thing is this AV is a conformal net. The other thing I should say that, as in the case of, I said there are many typically unitary structure, as in general for a simple complex Lie algebra there are many compact forms, but in a sense they are conjugates, so the unitary structure is not important. If you change the scalar product, then we get equivalent conformal net. So the conformal net really depend on the VOA and not on the unitary, on the scalar product. This is the first point. Second point is that this map is well behaved. So, for example, we have natural construction preserves strong locality. For example, this is very important. So if you take a strongly local, then you take a subalgebra, which is unitary, some stability condition, then this subalgebra will also be strongly local and will give what we call a subnet. Also, tensor product of strongly local is strongly local. Okay. And these are the first. Moreover, we have many examples. So the examples come from some traditional theorems from quantum field theory using these linear energy bounds. Linear energy bounds means the polynomial energy bounds when the power j is 1. This is very special, but we can use this together with these stability properties in order to get many other examples. So here just a list. So affinity algebras are okay. So the main point is the following. So maybe I should say this. When I define this, so the point is that we have here a lot of fields. And typically theorems that we have is for some special field. So what we show essentially, the main theorem, is that if we start here with the family, not the whole V, but the family of generators for the VOA, and we define von Neumann algebra from this, if this is local, then V is strongly local. So then locality for all the other fields come up. And this is one of the main technical results of our paper, and this allows us to give examples, because if not, this looks really very strong. So it's not so strong, it's what typically one has to do because of this theorem. So using this, we get many examples, and using subalgebra and so on, so all affine the algebras, every unitary, in all cases unitary, so the cosets, corresponding cosets, all orbifold subalgebras, unitary Virasoro VOAs, so for every central charge, sorry, the Virasoro, okay, then the known VOAs with central charge, unitary VOAs with central charge equal to 1, which are conjectured to be all, but we don't know, and the moonshine, okay, we also get a new example, which is this shorter, even shorter moonshine VOA, whose automorphism group is the baby monster, is another sporadic simple group in the classification. Okay, now almost finished the first part. Okay, I just explained how to go from VOA to conformal net, and the first question is, can we come back? And the result is, the answer is yes. So we come back if we start from a VOA. There is this, so there was a quite old paper 20 years ago around by Fredenhagen and Jors, and what they do in this paper, so they have an abstract, in a sense, general construction of certain fields, which are not really Whiteman fields, because they have some domain properties, but they look nice from their, from their covariance properties and so on. So this is a very general construction. You have a net, you can construct these fields, which are not Whiteman fields, which are not vertex operators, but they look like. And what we can show that if we start from a VOA, then actually this abstract construction actually give us back the primary, the quasi-primary. Quasi-primary means certain special vertex operator which are generating the quasi-primary vertex operator. So we can define, starting from AV, we get back D with all the structure. So, okay. And the idea, of course, in general, that in principle, if we do those in general, and we are happy, and then maybe this vertex operator algebra is always there. And actually, we have some condition on analytic bounds on these Fredenhagen-Jors fields, which guarantees the existence of this V, without assuming it from the beginning. Okay, but they are quite hard to check in abstract models, or in models. If you don't know that it comes from V, it's quite... Okay, but in any case, we have these two conjectures which are mainly empirical, because this does not mean that, okay, there do not exist counterexamples, but we are not able to, to construct them. There are also many models we are not able to prove that it's strongly local, but it seems that in some way one can arrange. And so the conjecture is, this first one is every simple unitary VOA is strongly local. And conjecture two, that every conformal net comes from strongly local VOA. So they should be the same things. And okay, here just quote some recent work in progress. I'm quite optimistic to this. And so we have to check something, but it's probably with not too many assumptions. It seems this conjecture 2, which actually looks in a sense harder, it looks harder because VOA is more explicit object, but actually maybe conjecture 2 is easiest to prove. And we have some step which also allows to give us new examples of strongly local. So, for example, unitary lattice VOAs, this was open as a conjecture. Unitary VOAs with central charge C less than 1. This we know because they are classified, but and there are clearly corresponding net which were found before by Cavagacci and Longo, but we don't know if they are connected in this strong way. Yes.
So the VOAs that you get from conformal nets whose FJ fields satisfy your conditions that you like, do they have some unifying property? Are they all some type or something like that. So you said you can construct the VOA from your conformal net if it satisfies the right properties.
No, what I say is, okay, this is, first what is sure is this. If I start from a VOA, which is strongly local, and I construct a conformal net, then this field gives back, okay. Then there is another result, which is in the same paper. We say, okay, if these Freudenhagen-Yor's fields satisfy certain energy bounds, which are the analogous of those we assume from the beginning in the VOA case, then again we can construct a VOA. Okay. The point is that these bounds are quite strong assumption. It's not strong, but okay, it should be equivalent, but it's strong to assume because it's hard to prove from a conformal net. It's easy to prove from vertex operator algebras, but since we start from a conformal net, we don't want to assume. So here we have some results in which we don't assume from the beginning the energy bounds, and then we get later. Okay, so first we construct the vertex operator algebra, and then we prove the energy bounds, and then go back to the net. But this is still okay. I think it's almost done, but okay, it's not. This is with Luca Tomassini, which is sitting here. Okay. Now I come to representation theory. So what I think is what is important is, in a sense, one of the hard part of our assumption is that we use all the fields. But this is the good thing to do, because it's thanks to this that we can go to subalgebras. So because typically if one starts with good generators and then go to a subalgebra, you lose the generators. And this is a frequent problem in VOA setting, for example, in study representation theory through generators. And so the fact that we don't use special generators but just use all the fields, it's actually very good to have examples. So now the idea is that, okay, this is what we should keep as a message also in the representation theory. This will allow us to go to both sub-VOA, so restriction representation sub-VOA, and both to sub-modules. So arrange to get many examples. Okay, so and this is the context of the following. So first start a representation of a net has been defined in some other talk before, various time. Just remember that's okay. It's essentially a family of representation PI. We have a representation of the algebra AI for each interval, and then there is this compatibility condition. So this family is compatible with isotony. So if you take the representation for a large interval and restrict to the algebra of the smaller interval, then we get a representation for the smaller interval. This very basic and natural definition. Maybe what I have to say here. Okay, this is a representation. Okay, representation in this way there are too many. That's really clear. This is a huge family, and one have to assume local normality, so that these are von Neumann algebra representations. They are continuous for the von Neumann algebra topology, and this essentially means that we are looking for representation on a separable Hilbert space. If the net is given first on a separable vacuum space, that I will always assume this. Okay. So this is the good representation theory. If not, there are no rational conformal net and nothing. Okay. We have to skip out the non-normal, non-locally normal representation. Okay. Then we can define direct sum, irreducible, and so on. And VOA, we have to look again. This is not so clear unless if we really have to assume, for example, in the rational case, but in general we have to assume because there are some VOA which are unitary, but which have some representation theory which is not unitary. So first of all, what is a representation theory? A representation of a VOA. So the idea is that, okay, here is V, is our VOA, and the module is a vector space, and the idea is that the fields, okay, act also in the module, respecting in a certain sense the structure. Okay, here the best way to do is, okay, write another set of axioms that instead of locality using Borcher's identity, okay, I don't give details, but there is a natural notion of what one calls vertex algebra module, okay, And then I will interest in both vertex algebra module and VOA module. So VOA module is a little bit more restrictive, and there is some semi-simplicity in so L0, the conformal Hamiltonian, one assumes that is diagonalizable, okay. And then one assumes that in a sense, that in a complex sense, the energy is bounded from below. So NH, which is the eigenspace for the conformal Hamiltonian eigenvalue H, is 0 if the real part of H is small enough, it's negative enough, okay? And moreover, one has finite dimension. This is a regularity property which is quite useful if one has to work with algebra only. Okay, and then we need unitary modules. So unitary module, there is a natural definition. This is was done by Dong and Lin. So we have a scalar product which is compatible in an appropriate sense, as a really natural sense, with the unitary structure of V. Okay, and when we have this, so each time we have a VOA module, we have a Virasoro algebra module, and in this case we get a unitary module for the Virasoro algebra as a special fact. Okay. Okay, V itself can be considered as a module. It's called the adjoint module, and this corresponds to the vacuum representation, what we call vacuum representation in conformal net setting. Okay. Now here it is an important trick that we will use, is that if you take a vertex algebra, so we have to look often with vertex algebra modules. This is because when you start with vertex operator algebra and restrict to a subalgebra, if the central charge is not the same, typically what we get in restricting is not a vertex operator algebra module, because some multiplicity go to become infinite, essentially, but it's just okay. It's just a vertex algebra module, but we need to use this kind of situation. So it's typically if you have a vertex algebra module and okay, W is a subalgebra, what happens that it restricts to again to a vertex algebra module, and if M was unitary, its restriction to W remains unitary. That's the point. So we can also define unitary module in this way. Okay, in general, V is not general, in general a VOA module for this W, if the energy, so typically they have different energy operators, so okay, so one has to carry a little bit about this, but this is a problem of multiplicities that typically one solves by using unitarity. Okay, now comes from what a representation is. So the message is, as I said, the vacuum tells what you have to say. So first of all, what we would like to have? We would like to have fields which are smeared and which act on the module. And again, we want to assume the energy bounds exactly in the same form, but for the vertex operators acting on the module and not on the vacuum. Okay, so we make the same assumption. These constants could depend on the module. This is not important. Although typically model do not depend. So we have general constants which are good for every model. Okay, again we can take an Hilbert space completion, and again we can define these closed operators. Now what we do with these closed operators? Okay, so typically we don't know. So again we give a definition which we think is the right one. So what should happen? So we have an operator in the vacuum. Maybe the main point is that when you have say a continuous representation of a von Neumann algebra, in a certain sense we can extend this representation to the unbounded operators affiliated with it, in a very precise sense, in a unique sense. This is the point. So the idea is take the representation and then we extend to these operators which are affiliated to the algebra. So this is Pi is defined on objects here. So this is not a good notation in a sense. It's abuse of notation because Pi of something is defined only when something is an element. What I'm guessing here with this notation is that I can extend to unbounded operator affiliated to this algebra. And this we can do. This is again a well-defined closed operator. And then we give it the definition. So the definition is simply this. So we ask that this, when a module is, say, strongly integrable, if, so we have this representation, is like a representation of the algebra. We are looking to a representation of the compact group, which is the net, say. And we say that the module is strongly integrable if there exists a representation Pm of the net associated with AB. Of course, we start with a strongly local V, such that this operator, which always exists, is equal, and which is closed, is equal to this other closed operator, which we define in another way using the energy bounds. So in this sense, the representation of the net connects, okay, the fields in a sense, in the fields in the vacuum, the fields in the representation. This is really natural, and we ask this to be true for every A in the algebra. Okay? And what we get...
Sorry, I'm a bit confused here. In the previous paragraph, you're saying pi L of y AF.
Here, this pi I.
Pi I.
Yes, so pi I, so we have a function in support in I. Yeah. So this, I just maybe write few. So we have, this is the smeared vertex operator acting on the vacuum, so on HV. And this is an element, is a closed operator affiliated to this von Neumann algebra. Okay?
So that you're saying that will...
Then, so pi A, this is unbounded. Yeah. But pi A, y, AF makes sense. Typically, this is unitary implemented. So this is just a unitary, you have a unitary map here. And it's perfectly well-defined closed operator. Okay, what we ask, and we have another operator, which is defined directly in the module, because in the module we have a field acting from the VOA theory, and what we ask is, this is the same field. So the field in the module is connected to the field in the representation through the net representation. Of course, look, this is the definition, so I'm not claiming that there exists, so I am asking that. I say this is strongly local, integrable if such representation exists. And then next step is to give examples, because it could be empty.
What's the right-hand side, ym of AF, the right-hand side here? In the definition, right? What's the right-hand side of that equality?
Yes, these, I don't know if I use the same notation, yes. So when you have, maybe go, you can see there, you can see, okay. So by definition, a VOA module is a vector space, and then I gave not the complete definition, it's a vector space, but acting on this, there are fields. Fields means, again, formal power series associated to the module, and the entry here is in B. So in a certain sense, this is the field coming from the vacuum representation, and there is a corresponding field in the representation space.
Fine.
That's the, so this we have, and if we assume energy bounds, we can smear also these with test function, with smooth function. So we have one closed operator coming directly from the module, and one other coming from the representation of the net and the vertex, smear vertex operator in the vacuum. And we have to assume that they are the same. It's exactly,
And why can't you just define pi L to be ym of AF?
This. Why can define this?
Define the left side to be the right side.
Yes, this is. So this is a closed operator. So take maybe more abstractly. If we have we have a fundamental algebra and we have a normal star morphing, okay, from n to n, okay, let's take A, which is an operator, closed operator affiliated with n, okay, then we have a polar decomposition. So A is equal to partial isometry times the modulo of A. And this is self-adjoint and this is bounded.
I know, quite well, yeah.
Huh?
Yeah, I'm quite familiar with
No, this is the definition. So I can, so I just define, I know, but this is just this. So I can define phi A. This is the definition, is quite natural definition. Phi V times phi the modulus of A. In this sense, I want. Okay, one can show that this is a well-defined closed operator whose polar.
It seems like what your definition is saying
Maybe
that
the
you're
point is that
assuming that ym of AF has the right properties.
but maybe the point is that pi I is a representation of the net.
No, pi I is the representation of the net.
Yeah, but
So it's phi. Yeah.
why doesn't ym of AF give you a representation?
This I don't know. I'm assuming that there
Oh,
exists
you-
a representation with this property.
So your assumption is that ym of AF gives you a representation of the net.
Yes, but I am okay. This is
So you're assuming
okay. No. So I say another thing. This is if I typically try to give this definition, this is something terrible. So I say assume that this should be the good. So if they correspond, they should be like that. So they should correspond. So from a module, we should have a representation with this property. Of course, it's not obvious at all that it exists.
You're assuming basically what you want to happen.
Yes, but this is a definition. So maybe you're saying you don't like that I give definition before to give example, and this is right position. It's sometimes reverse, and I give first the definition and then I give the example. So I have the example. So
So the two representations, one is the net, the other one is VOA.
it's a VOA, and I say okay, if there is a so what should be a representation of? So I start with the representation of the model. I say what should be the definition for a good representation of the net corresponding to it. I say if there is something good, it should satisfy this. And this completely determines the representation. I don't know if it exists, but the definition is, it defines uniquely. It's clear?
So it sounds like you're just saying, oh, we're going to assume what we want. Without having any examples, you're just saying, oh, we're
Yes,
gonna
the example is the next page.
we're going to assume this construction works.
No, yes, so it is just, but example is in the next slide. Okay, no, you're right, of course, I have to give example, but in a VOA case, we do the same. We first give the definition and then the example. Why? Because we have to know what we really want to prove before to find the examples. No, if this was the idea. I understand it could be confusing, but, oops, sorry. So because we want to prove some general results that then we use to give examples. This is the idea. For example, if you start with, okay, first of all, well, for example, we have various examples. We start from strongly local, and this is a category. Worry is not, nothing is said about the tensor product in the category. It's just as a category of a linear category. So, as a category of representation, so this is a subcategory of the VOA category of representation, and we have a functor. And then we can prove this, that, first of all, this is, okay, given M there is a unique PM. So I don't know if it exists, but if it exists, it's unique. So this symbol is well defined. And if you have two, and okay, the isomorphism is the same from the VOA point of view, and okay, we have unitary equivalence from the conformal net setting. Okay, of course, by definition of strongly local, this strongly local just means that the vacuum module is strongly integrable, and essentially, okay, and then this is the rule for basic things for the construction. If you take a subalgebra, so you take a V and then you take a W, which is a unitary subalgebra, and you take a strongly integrable view module for V, then every VOA, so then W acts on M, and I take, there are some acts on M, in general M is a vertex algebra module. I take some VOA submodule, M tilde of M, and this is again strongly integrable for W, and this is a way to get many examples. Okay, this is similar to the way we get examples for conformal nets. And then take the, okay, this map is a one-to-one correspondence between the submodule M tilde of M and the subrepresentation of Pm. Not that here the strong thing is that I am assuming that M, from the beginning, the big one, is strongly integrable. If not, this result is meaningless. Okay? And then we can use this to give example. So the reason why we first give a definition and then give example is that we want to have a little more structure in order to be clear on the proofs. And the examples come from fermions. Actually, essentially, we do something similar Anthony Wasserman is doing. Actually, is inspiring from that, because we were looking to specific example, because when we have done this, we had in mind some specific application coming from Feng Shui work, so we were looking for specific example, but we found this situation to look quite general, the good definition, so we gave us a general definition. Then we will see how many examples we can find. And the example here I'm looking for is just to take the affine. This is SUN level K, which from the point of view of the algebra comes with this SL matfrak, okay? And then there is a unitary affine the algebra, which is, we know it is strongly local from the previous work with Kavegashi, Long and Weiner, okay? And then the corresponding net is the loop group net, for example, okay, which quite well known and can be defined directly from the representation theory of the loop group. Okay, we just define directly with the vertex operator algebra. Okay, then this point is that we have another. Okay, Vn actually is a vertex operator superalgebra. You know, the definition is there is no locality axiom, which is a sort of Fermi locality. But we avoid this. There is even VOAs subalgebra, which is a true vertex operator algebra, and V plus is simple and unitary. Okay, and then we can show what? So, okay, we can show various things. Okay, this is known. So we take this VSLN at level K. This can be embedded as a unitary subalgebra in V plus, so in the even part of the fermion times 2nk. I think maybe I'm using here real fermions, okay? So this 2n correspond to one complex fermion. But this is essentially what Anthony Wasserman used in proving his fusion rule. So it's a part of what he was done. So I use fermions. Why I use fermions? Because fermions are easy to get analysis because we get bounded operators. So we embed this in submodule. So the point is that this V plus is a strongly local VOA. This is quite easy to prove, and it is shown also by James Tanner independently, but it's quite basic, so it's quite easy fact to show. And then that the modules, so V, the full superalgebra, is a strongly integrable module. Also, this is quite easy to prove. And then from this, we go through the subalgebra and to submodules, and we get a lot of examples. In particular, we get examples for, take a V is a sort of like SUN1 at level K1 times SUN2 at level K2 and so on. And this is the corresponding vertex algebra. And then all these, in this case, for these nets, which are very special but interesting examples, we all have, all these modules are strongly integrable, so the representation PM exists. Okay? Okay, I think we were interested on this, so these are the examples I give here, but it's quite clear that there exist many other, and we just not written because we were interested on this. So why we were interested on this? This was the motivation for our work. So there is a special case of looking for embeddings like this. This is diagonal embeddings. We take tensor product and then we embed with the sum of the level. This is called diagonal. Okay, using this. And then we can consider the coset. The coset is a construction, is a standard construction that we have both in vertex operator algebras than in conformal net setting. And the point is that we have shown in the first paper that they correspond. So in the paper with Yasu and Roberto and Mishi. Okay, so we have this corresponding inclusion of nets, which correspond to something which were studied before by Feng Shu many years ago. 5 minutes, it's almost finished. Okay, so I will be a little bit rapid. So what was the motivation? So Feng Shu, by his study of cosets using subfactor theory and many analysis, have given a very detailed description of the representation theory of this coset net. Okay, and there is something which is, he has some results which are still unproven after many years in the VOA setting. Okay, because this is a problem of generators. Okay, yes, this result, and the point was, can we transfer the resulting conformal net to VOA? So this was the motivating fact, and the point is that we can transfer them. So we have new result in VOA representation theory, so purely algebraic results coming from functional analysis. This, I think, is very often we do the converse. So we start from algebra and go to analysis, and sometimes we can do this in a very effective way. So maybe I just here I have to skip because the time is close, but that maybe okay. So one should say something detailed, but here there is example. So, okay, in the case of 2 and a very special case in which one level is 1, we get a series of sorry. Okay, you know that I will thank you. So there is a series of modules of the cosets, for not of all, but I think for many, it was open if they are irreducible. You get very easily to give a definition, but you cannot study irreducibility easily. This is one of the results, and in this case, since we have the corresponding result for the net module, we can transfer and we get this. This is algebra, pure algebra representation here. Okay, and this seems to be a long-standing problem. I'm not so expert, but Feng said that it's still open. I don't know now, but some few months ago was open. In any case, I don't think they will solve with the same proof. Okay, so thank you.
Any questions?
Can you just show that slide that you went over very quickly?
Yes, you're right. Maybe this one. Okay, so this is the situation studied by Feng. Just translated with, instead of putting the loop group, I just put the VOA notation, but these are the same nets. It's just, and this is the situation in VOA. So the idea is you have this embedding, you take a module from this big one, and you decompose, so we have a subalgebra, and then you have a coset. And then this can be, the coset and the subalgebra stay in tensor product position, say. So we can restrict the module for the big one to a module to this subalgebra, and get something like that. These are well-known modules, and these are modules for the coset. And the question is, what you know about them? Okay, this is one of the things we can learn about it.
So for story, is it important that you have the conformal covariance of the Virasoro algebra, or just maybe
So I think that many things so there are many problems. So when you have property, you use them and you don't know exactly. So for conformal covariance, energy bound, many things we can drop, but we have to check. And I think that typically Moebius covariance should be enough for many things. But I'm sure that we use when you have Virasoro, you use. So maybe you can avoid, but just you have to check. So I don't know. In this case, I think it's not crucial. The definition works, so you have to check things. Okay. Actually, we also know that in these examples this is automatic, so why avoid it? Okay.
So you mentioned that for the lattice, you need a strong locality. But I thought in the case of lattice, it's just a loop group with target space torus. In that case, you should follow from the Bosonic.
You say that a strong locality for lattice is, you can...
Because the lattice is just a loop group where the compact group is just a torus. So I think in this case, maybe there's an easy proof.
No, yes, this is a point. So, yes, it's not so clear because you're right, but since this is not connected, so up to the current, you have some footer vertex operator, and you have to study that. In fact, it has the Rice analytic property. This is what I expect, but I think we can prove in other ways. Probably you can prove also in other. If you look at Karp's book, this operator is not clear that you manage from commutation relation to get easily energy bounds and to prove what you want. I think you should. It's okay.
And how about strong additivity? So when do you see it at the level of vertex
Okay.
operator algebra?
Strong additivity, one can have a very easy sufficient criterion, which is the following. If you have the vertex operator algebra is generated by V1, so fields of dimension 1, and Virasoro fields with central charge less than 1, then you get strong additivity. This seems to be very special, but you get really many, many examples. And then you have to use other theorems by Roberto Fengen to get extension, so you get many, many others. But it's quite easy to get strong additivity in this way. For example, for loop groups, you immediately have. Of course, it is known for loop groups, but just to, is another proof, but actually it's the same thing. You use essentially this. When you know that you get strong additivity, then you use it and to transport to many other examples. So it's quite easy, but I'm sure that there are a lot of examples that you can show and that you don't know if it's strongly additivity or not, if it satisfies it or not. So it depends on what you need. Strong additivity could be very, very hard, but now we have a lot of criterion, so.
All right, so let's thank Sebastiano again.